welcome to the Cairn Research virtual booth. I'm Ros Davis, Sales Coordinator at Cairn, and this is Jez Graham, our CEO. So in this video, we're going to introduce you to the openFrame sustainable microscope concept, which was conceived by Professor Paul French at Imperial College London, co-developed and supported by us at Cairn Research.
So what is the openFrame? The openFrame is a stable, sustainable and affordable platform that enables us or other companies or labs to build highly optimized application-based microscope solutions. Everything is centered around the objective lens and full optimization of the infinity space. How would I go about getting one? Well, there's a few options. Because it's an open source project with Imperial College, the CAD files are available to download from the openscopes.com website. Alternatively, for self-builders, we're happy to provide machined aluminium components, building blocks. But what we hope in most cases, and this is proven to be the case, is that we will talk to researchers who have particular requirements and help them to assemble a dedicated applications-based scope to solve their experimental problems, either using our own dedicated modules, incorporating equipment that they already have, adding new third-party components, or doing an element of custom design to solve the problems.
Yeah, and here's one example of that, which we're going to go into more detail of later. In this next clip, we're just going to illustrate the modular format of the openFrame. So enjoy. Here you can see the layer-by-layer build of the openFrame, illustrating the modular format. Each layer can be positioned at a range of angles at any 45-degree increment. Right, now that you've seen the build, let's talk you through the details. Starting at the top, we've got our stage adapter layer. It's currently fitted with a Nikon manual stage, but it has mounting points for all popular microscope stages, both manual and motorised.
Moving down the openFrame, we get to the guts of the instrument. So this is the whole point of the openFrame is it's centered around the objective and around a single optical train in infinity pathway. So this focus layer has houses the objective. We base it on a single long travel axis. In most cases, this will be a motorised linear stage that we've developed specifically for the purpose, like a fully encoded high-speed stage. In this instance, we've got a differential micrometer, so this is for a sort of low-cost version. We'll be showing the high-end, fully automated microscope at the meeting in our lecture slot. So this is the focus layer, the guts of the instrument. One nice thing about the focus layer is it also has the opportunity to bring in an epi source or an autofocus source within this layer.
And moving down, this is one of our bread and butter layers, the 65mm layer. See on each side it has two mounting points with an SM30 tube bore and 30mm cage output, so you can mount a range of different components. We predominantly use this layer for epifluorescence, so as you'd expect, there's a filter cube in the middle. Over here, so we've got two versions. This one here, it supports our 32mm cubes, and we've got this other one which supports our smaller 25mm filter cubes, which is just magnetically held in place, so it's nice and easy to work with. And then these just slot in again, magnetically registered, nice and simple. Below that we've got the smaller 30mm layer, this houses the tube lens. We're currently working with a range of options, predominantly the large field of view Nikon and Olympus, as well as a range of Thor Labs tube lenses, and we're also working on designing our own one.
So moving down to the bottom of the instrument, you can see here we've got a C-mount adapter camera port on one side. We can equally well fit a camera port on the other side. We have either an individual holder, which I've got on here, which can be fitted in the front or the back, depending on which camera you want to divert it to. So that's the kind of low cost version. For those with more of a budget or more requirement for 2 cameras simultaneously, for example, if they're using a colour camera in lieu of the eyepieces that are manifestly missing from this microscope, quite deliberately, then we have a 2-position slider, so we can go from left to right automatically. One thing that we should have mentioned, or we are mentioning now, is that there is no back or front of the openFrame. So every layer can be orientated in any of preset 45-degree positions, or if you need to do something more esoteric, then the locator pins can be taken out. And the whole below the camera layer, there's a solid base that has mounting holes, both slots and holes to mount onto the optical breadboard. And the central axis of the openFrame, I'll show you, is all based around a 2-inch clear aperture. And this goes right from the top to the bottom. So in order to orientate the system and to ensure that the microscope is really optimised for very precise applications such as turf, then we can put laser alignment tools both on the top and the bottom, and align the optical axis so that light passes straight through the objective, through the centre of the tube lens into the centre of a target below. This can also be done on the side ports, because the camera mirrors have fine adjustment, so we can completely align the optical axis to the side as well. So the whole idea is that we can really optimise everything very precisely if necessary, but of course for many wide-field applications you can just go with it, you don't need to do any of this stuff. So we've introduced the basic components. Now we're going to talk about a few of the modules that we've developed for the openFrame, and also some of our other components that we have been used with conventional microscopes, but we are now using increasingly with this platform.
Hello again. Now we're going to just run through a couple of different configurations with our range of image splitters and light sources. Off we go.
So, starting with the OptiSplit 2 bypass, hopefully some of you will be familiar with this. It's an image splitter designed to do simultaneous 2-colour imaging on a single camera sensor. It has a very neat, convenient bypass mode, has individual filter positions for adding filters over and above filters that are incorporated into the fluorescence cube. This one is configured with a C-mount camera, but we support larger formats and can fit T or F mount, or even dedicated mounts for bespoke cameras such as the Photometrics Kinetics.
And that's the same on both the input, that can be configured C-mount, F-mount or T-mount. And here we have the triple split, the next one up in our splitter range. Like the OptiSplit 2, instead this is designed to split the image 3 ways onto the camera chip side by side. It also has component holders so that you can introduce deliberate focal shifts, or it's an extra place to help to put your filters. It's got our 3-way splitter cube, which uses our Chroma Ultra Flat Dichroics and standard 25mm. It's just got a dovetail mechanism to hold it in place. And the same with other ones, we can use it to support F-mount cameras on request. Yeah, and
Moving on.
moving on.
And for those of you where 3 colours isn't enough, we're very proud to present the multi-split image splitter, which divides the fluorescence signal or other signal from the microscope into 4 discrete channels. It comprises of a set of 3 independent filter cubes, so we can completely configure the separation of the different channels of light using fluorescence, polarisation, or just neutral beam splitters. As with our other splitters, we have individual component positions. With 4 colours, the requirement to do chromatic correction between channels becomes more paramount because it's likely to be an infrared channel and a blue channel, and there can be a reasonable chromatic separation. So these positions here allow you to insert lenses in to correct the focus between them. One of the issues, of course, of dividing the signal up into 4 quadrants on the camera is that it has a corresponding detrimental effect on the field of view. So we've designed this specifically to work with the very large cameras such as the Andor Sonar and the Photometrics Kinetics.
Right, and now we move on to the cams. So starting with our twin cam, as you can see, it supports 2 cameras. Beauty of this compared to our image splitters, the Split 2, is you can use the full chip of the camera, and this version supports cameras up to 22mm, but we also have a large diaphragm, F-mount output so that we can support up to 25mm field of view.
Large version of the diaphragm to support the 25mm diagonal cameras.
Yep. And then so predominantly use this for 2 colour image splitting, but you can use polarising beam splitters, or just plain percentage beam splitters if that's what you want to do.
So as cameras have become cheaper and CMOS technology has taken over and moved down the price point, then there's circumstances whereby you can get away with a somewhat less expensive camera, and you can achieve the multi-channel high-speed solution by multiplexing the number of cameras rather than splitting the chip up of a given sensor. So on this configuration, this could actually be set up for 4 cameras. At the moment we've got it set up for 3, so this is what we would call a triple cam configuration, and these cameras are actually a camera that we've developed recently and will be launching very shortly. They've already gone out to a lot of early adopters and have been very well received. So we'll be adding to this camera range in due course. Watch this space. As with the twin cam, we have individual cubes, we have XY alignment, very precise pixel alignment of the different channels. We can insert filters, we can have filters in the filter cube, and we can support fields of view up to 22 at a pinch 25mm diagonal. Anything to add, Russ?
No, I think you've got it well covered there. We can move on to one of our more fancy cams now with some integrated wheels.
Okay, so as Rosanna mentioned, with our twin cams and our splitters, we can do all kinds of tricks with them by combining them. So we can combine twin cams and splitters and have an unsplit image on one camera and a split image on another camera. The other thing we can do, if you're not want to be constrained to a particular colour, is we can combine these multi-camera adapters with our high-speed filter wheel. This is actually set up to fit on a Nikon microscope. So although we're very proud of the openFrame, we also completely understand that there's a place for conventional microscope frames, particularly where you want to have multiple users or multiple modulations on the modes of operation on the same scope. This demonstrates the extended field of view. So we've got F-mount, so we can fit 25mm diagonal cameras onto this version. So it's dual camera, single controller, and single controller to drive 2 fast filter wheels.
Indeed, and in addition to our OptiSpin 25, which as the name suggests fits 25mm filter wheels, we also offer our OptiSpin 32, which houses 32mm wheels. This could equally be integrated into this system or onto the side port of the microscope to support the 25mm sensors.
So all these detection devices that we've just shown are designed to work around either openFrame or a conventional microscope. We're now going to talk about a couple of illumination devices and then show 1 or 2 modules that we've developed specifically for the openFrame architecture.
Alright, I'm going to talk about a couple of our light sources as well as some of our custom built modules that we've done specifically for the openFrame. So here you can see our Fura LED head, which is a dedicated dual wavelength Fura 2 illuminator at 340 and 380. It's a lovely compact module, so it works very well with the openFrame. As you can see, it fills up the module space nicely without interfering with too much. Most people are going to want to do other dyes other than Fura 2, so we've also got our twin LED housing. Same footprint, it tends to have visible wavelengths in here. So for example, we've got blue and white in here to cover most common dyes. You might be thinking, oh, you've taken up the epi port, so where are you going to put this? Well, we've got a couple of places it can go. So they've got the dual infinity slider under here, so it can just be mounted on the back, so you can't see it because it's not clashing with anything. It can also go onto the focus layer on this side. On this side, as Jez mentioned earlier, there's still space in there to bring in an extra light source. Right, and that brings me on to the dual infinity slider here. It's kind of handy to be able to switch between a couple of different filter cubes. Like if you've got the twin LED, for example, you might want a dedicated GFP cube and a dedicated M-Cherry cube instead of a dual one. So this will allow you to do that. I'll just show you the insides. Right, so as you can see here, I've just fitted it with 1 cube at the moment. It's our own design of Olympus style filter cube. It's got a clever little slider mechanism with 2 filter cubes and 1 blank. It's quite electrophysiology friendly. So it's got a bit of a bounce back mechanism on the slider, so it's not too clunky. Don't know if that shows it well. It's very easy to change filters in and out. As you can see, it's held in place magnetically, so it just slots back in, tightens up, and then you're good to go. Right, over to you, Jez.
So just to summarise on the initial openFrame we've been showing things on, this is a fairly standard configuration, but even in this standard configuration we've got three different levels of access to the infinity space before the tube lens. In this kind of configuration, it will fill the field of view of a standard SCMOS sensor. For the very large sensors, it would be preferable to restrict it to two layers, as the field is dependent on the length of the infinity space. So this is a triple stacked layer. We're now going to show you another microscope that we've made specifically for being rather simple and compact, and it has a few additional features that we haven't covered so far. Anyway, so this is a rather interesting configuration of the openFrame. So the brief in this case was that we wanted to be able to have more than one objective, so we had to make a objective carousel available. We also had a target of making it quite affordable and compact, so we stuck to this very kind of squat configuration. We've dealt with the sample preparation by designing and building a magnetic slide holder with X, Y, Z micrometer control of the sample. We've also included this nice magnetic sliding mechanism so that you can pre-position the area of interest of the slide so that you don't have to move the XY micrometers too far. So this configuration is set up for transmitted illumination using our condenser-free Aura condenser, LED-based phase ring illuminator. This device can do phase contrast and also dark field and conventional bright field, depending on whereabouts you position the phase ring on the pillar. So if we come in close, we get dark field. If we move further away, we get bright field, then phase, and then bright field towards the centre of the objective. And we can provide more. Please contact us if you want more information about the Aura phase contrast illuminator. We've also included a standard transmitted LED for the middle, so you can use other techniques. Pillar folds out rather nicely. And this device, although designed to fit very nicely on the openFrame, will also fit onto any conventional inverted microscope frame. We've set this system up with a twin cam with two of our low-cost CMOS cameras, and we're going to miraculously connect up a computer and show you a little bit of fluorescence and transmitted imaging.
Right, we're back. As you can see, we've now set up the system. So we've got a twin cam fitted with two cell cam monos, along with our twin LED dual illuminator with blue and white LEDs. So I'm just going to switch to a fluorescent slide now. It's just a simple tree roots, just for illustrative purposes. It's not set up at the moment, as you can see. It's a bit wonky, so I'm just going to adjust that to bring the two channels overlaid.
There you go, well done.
Right, there we go. I think that camera is still a little bit wonky.
It only takes a couple of seconds to align, really.
Yeah.
Famous last words.
I know, it's the pressure. There we go.
Okay, I think we can open that up.
Yep.
So we then open up the aperture to just overfill the camera chip, which reduces any potential background or light bouncing off area peripheral to the chip.
You might still be thinking, hang on a minute, that's not very well overlaid. That's just because when you start it up, one of the cameras will be flipped relative to the other. But there's a helpful tool in the micromanager software that Jez is just going to show.
Which looks like it's set up there. Yep.
Yeah, it's just called Image Flipper, isn't it?
Yeah, Image Flipper, and now you've got it.
Yeah, in the correct orientation. Very nice and simple.
So that's the twin cam. The other main thing that we've got on here that we haven't really shown you properly is the Aura phase illuminator. So if I turn off the fluorescence and go to a white lookup table to show things a bit more clearly. And turn up the illumination a little bit. You'll see that this is a ring illuminator, so it has 3 rings, which can be any colour: blue, green, red, infrared, whatever you want. And it also has a central channel if you want to do any kind of conventional illumination. The centre channel can also be used for imaging because we don't have eyepieces. If you want to use either a low magnification objective lens or a machine vision camera lens, in the centre you can get an overview of your samples from above. But what I'm showing you now is the aura. So if I move to the bottom of the height, we're bringing light in from the LED ring at angles beyond the acceptance angle of the objective. So we're getting a kind of dark field, but you can see as we move further out we get better dark field contrast, a better idea of the structures. As we move it further up, we're coming within the aperture of the lens, so we're getting sort of standard bright field transmitted light. So there's a slight tweak on the focus, and then you can see as we come up, we're starting to align with the phase ring and seeing some increased contrast from the fact it's a phase objective. So it's rather a neat illuminator. You can pick out different structures and essentially get more maximise the contrast you want. We're very pleased with this simple microscope. Basically everything's adjusted with micrometers. We've got magnetic slider for doing coarse macro adjusters to get the thing vaguely in the right place. I've lost it there. And then once we find it. Tell you what, it's not moving. Just 1 second. There we go. There we go. That took a while. But then once you've got the sample in the field of view, then you've got X, Y, and Z adjustment. So hopefully this has been interesting for you. We've shown you today a couple of different configurations for manual open frames, but we will be, during the meeting, we will be presenting a talk on a fully automated system, which is the way that we expect most systems to be built. We just thought it was quite fun to show you the lower cost manual builds today. So I think we're just going to summarise and finish off.
Yeah, so I'm just going to run you through a few points of why we love the openFrame and why we hope you'll consider it for your next project. So the first major point we consider is the sustainability. We hate seeing microscopes that are just out of use, stuck on a shelf, or even worse, in landfill. So we hope the openFrame will address that. Pretty much because you can buy what you want when you want. So this is configured for one particular setup, but so you don't need to do that anymore. Instead of putting it on the shelf, you can buy some cheap bits to transform it into a new application of your choice.
Or importantly, to reuse bits that you may already have.
Yeah, exactly.
So it can accommodate old stages, light sources, objective lenses, filters, anything really. They don't even have to be in the right cubes. We can cope with anything.
Exactly.
Along the lines of the sustainability is the affordability. It's affordable partly because it just doesn't have any additional complexity. It's a single optical axis, completely accessible infinity space, and you just buy what you need. You don't need to think about where your experiments are going to go because you know full well that you can extend and expand to do to meet future requirements.
And then another point is it's optimizable, so you can test it up to match exactly what you want to do. For example, we could have the Pure LED mounted on the top here. You could optimize it with UV optics and then have a more visible wavelength light source further down, which is optimized for those wavelengths. It keeps it as good as it can be.
It's very compact. Hopefully that's come across in this presentation. One of the key things about the compactness is that it doesn't have a front, a back, or a side. So every layer can be orientated in any of 45-degree position. Where it's really critical, I think, for saving your space in your lab is the fact that it can fit. It can be built to be wide where light comes in from one side and out from the other, or some combination thereof. So we don't need any depth. So it can fit on a sort of standard worktop bench without requiring access from behind.
And then another point is that it's laser safe, where it's not got any eyepieces, so there's no chance you're going to blast yourself with laser light, which no one wants. You also don't have to deal with the cost and complexity of making the frame laser safe. Another point is because there's no eyepieces, it makes it a lot more COVID secure because there's not going to be multiple users kind of getting in there.
side to side, and then you can easily clean the Unix where it's in individual layers. You can just remove them, clean them, put them back. It's all very straightforward.
And finally, we should say that we don't purport to have solved all the problems that there are. If you have an application that you want to work on, you can buy the basic openFrame. You can take an open source 65 or 80mm layer and then build your entire optical system on that. Cage mounting, thread mounting, 2-inch 30mm and 25mm optics. Really knock yourself out. And if you've got multiple PhD students with different projects, they can build off in different directions. So the same stage objective camera can be used by 2 students, one in the morning, one in the afternoon, without any compromise of the individual optimization of their system. So hopefully that's given you a little bit of an introduction into the openFrame and why we're so keen to get involved with the Imperial Group to develop it and to make it a reality. Enjoy MMC. We'll be around.
Yep, I'll be on the live chat to answer any of your questions, and we hope to hear from you soon. Thanks for listening.
Thanks very much.